All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Wednesday, October the 30th?
30th.
Holy cow, October the 30th. Okay, Lucas, what are they supposed to do if they're liking these videos?
Smash that subscribe button, hit that like button,
And
the little bell.
yeah, that. All right, so just to tie up what we talked about yesterday, we were talking about nuclear power plants. There are three main components to a nuclear power plant. The most important part are the fuel rods. What is the fuel in a nuclear reactor?
Uranium.
Uranium what?
235.
Pellets, but it's 235. You're going to raise your hand when I start calling you. Okay, uranium 235 is pellets. Now, what do they have to do to those pellets to get them ready for the reactor? Anybody else? Is most uranium in the world uranium 235?
They have to enrich the.
They have to enrich it. What is the percent in nuclear fuel?
3 to 4%.
3 to 4%. Nature only it's about 0.7%. Maybe even less than that. It might only be like 0.239. What is it in your notes? What does it say in your notes as far as in nature?
It's like 1 0.
Huh? Does it say 0.7? Okay. So we have to enrich it, and that's what the government does, 3 to 4%. Now, when the rest of the class gets here tomorrow, we'll go back and we'll start talking about an atomic bomb and how it works. As far as you have to have 90 to 95% enriched uranium in order for it to be a chain reaction explosion bomb. So at a nuclear fuel, yeah, you can have an accident, you can have a meltdown, you can have bad things happen, but you're not going to get an explosion like Chernobyl or Nagasaki at a nuclear power station. You don't have enough enriched uranium present in order to be able to do that. So we have our fuel in the fuel rods, the uranium-235, being bombarded by neutrons, and it's the neutrons that control the reaction. But then it's surrounded by water. What do we have to do to the neutrons to get them to be absorbed into the nucleus? It's got to be somebody else. Okay? What do you have to do to the neutron to get it absorbed? Go ahead, Lucas.
Put it in a centrifuge.
No, that's how we separate it. That's how we enrich it. But what is the function of the water besides cooling? What does the water do to the neutron?
Absorbs radiation.
No, it does do all that, but that's not what it's doing to the neutron. What's another part? Look in your notes. What's another part of the reactor?
Nuclear. Cooling.
You're just talking. Just wait until you get something actually an answer. Get your notes out and look.
What's the question?
What does the water do to the neutron? What do you have to do to the neutron in order to get it to absorb into the nucleus? Okay, I'm going to give you a clue. The water acts like a moderator. So in your notes, what does the moderator do?
Slow down neutrons.
It's why. What does it say there?
So they can be absorbed by the nucleus.
So they can be absorbed by the nucleus. The water acts like a moderator. It has to slow the neutron down. Okay, it's right after the nuclear fuel. Okay, so the moderators slow the neutrons down because if they're going too fast, they actually go right through the nucleus. So as it goes from this fuel rod to this fuel rod, as the neutron goes through the water, it slows down enough to where it then gets absorbed by another uranium-238. Otherwise, it just goes right through. In Chernobyl, they used graphite, which it's a solid. It was the very first type. It's called an RBMK reactor, but it was this huge, just cube of graphite. I mean, like half the size of this room, type thing. And then they would put the control rods just into it, in little holes that were drilled into it, and they were separated. And so as the neutrons went from one fuel rod to the next, they would go through the graphite, and the graphite would slow it down, and then it would get absorbed on the other one. That's the very first type that was formed. That's what Enrico Fermi did in under the University of Chicago, under the stadium. He built the very first one of those. It is out of graphite, but it's very primitive, and it's the graphite that caught on fire, and that caused the big explosion in Chernobyl, and it was very difficult to put out, and it was just a mess. We don't have any of those here in the United States. That was the very first generation of nuclear power plants. We now use water, just normal water, as our moderator. So the water surrounds the fuel rods, and it does two things. It keeps it cool, because we can see here, this is the cooler water coming in. Okay, the water gets heated up, so the water is the kind of the conduit for the heat, but it's cool water here, hot water coming out the top, so it's got that function, but it's also acting as the moderator, slowing the neutrons down as they go in between the fuel rods. Okay, and then lastly, you have these control rods. So what do you think the control rods do? Come on, this is advanced level class. What do you think control rods do?
They control it.
They control the reaction. They control the reaction by controlling the neutron population. It's the neutrons that cause all the fission. It's when the uranium-235 absorbs a neutron, it explodes. So if there are no neutrons, there are no spontaneous fission. So the control rods are made out of boron or cadmium. The neutrons just stick to it. The reality is there's a bunch of boron in the water too, and they can control the neutron population just by the concentration of the boron in the water. But if they need to shut the reaction down, they just drop these control rods down in between the fuel rods, and then that catches all the neutrons, and everything stops.
Wait, you said boron or what?
Cadmium, CD. This is cadmium, element number 48. Boron and cadmium are what the control rods are. Neutrons just kind of stick to it like flies on flypaper. There's just a natural affinity for the neutrons. So we can, in the reactor, you have the fuel rods themselves. That's the uranium-235, the enriched. You have the moderator that's got to slow the neutrons down. That's the water. And then you have the control rods that control the neutron population, because if the reactor is going too fast, you want to absorb some of the neutrons. If it's going too slow, you let the control rods up and the reaction goes faster. And they really do most of the controlling with the boron concentration in the actual water surrounding it. So then this water's hot. It, by conduction, heats up this water, turns into steam, and then all electricity, the steam turns the turbine, turns the generator, makes the lights in the house come on. Okay? So if you're in a coal burning power plant or a natural gas burning power plant, instead of using this nuclear reaction here, they're just going to burn coal or burn oil, burn coal and natural gas. It's going to produce steam. Steam's going to turn the turbine, turn the generator, produce electricity. It's all about making steam. And we already learned at the beginning of the year, it takes a lot of energy to make water boil, to break those hydrogen bonds, break those water molecules apart from one another. Remember when we did the Q1, Q2, Q3, Q4, and Q5, the Q for boiling was about 75 to 78% of the total energy to take it from ice to steam. It takes a lot of energy. Nuclear power is the most efficient, most cost-effective, most environmentally friendly way to do that. Okay? So you just need to know the three main components. Fuel rods, using uranium-235. The moderator. Chernobyl used graphite. We used water. Canada sometimes uses heavy water. Okay, and let me just explain what heavy water is, and then we're going to go on. Heavy water. Anybody know? Okay? It's probably water that weighs more. We know that water technically is H2O, right?
Right.
So we have hydrogen 1, which we call protium. 99.985% of all the hydrogen in the world is hydrogen 1. Well, hydrogen 1 has a molar mass of 1.0 something 0.07 something grams per mole. Well, hydrogen 2 is called deuterium. Now again, remember, we talked about this earlier, but hydrogen's the only one where the isotopes actually have a name. Every other isotope's just a number. But hydrogen 2 is deuterium for deuce, meaning 2. Well, obviously, what's the composition of hydrogen 1 atom? How many protons, how many neutrons? One what?
One proton.
And how many neutrons?
0.
0. Okay, somebody else. Hydrogen 2, what's the composition of the nucleus? Is it 2 protons? Because that would be helium. What's hydrogen 2 going to be? What's this mass number tell me? Go. 1 proton, 1 neutron. So hydrogen 2 just has an extra has a neutron where this one doesn't. But neutrons and protons weigh about the same amount, which means that the molar mass of this one is about 2.0 something grams per mole. Okay? Now the average is 1.0079, which is what's on the periodic table, because we have majority of this one. So most water, if you go fill up a cup of water, majority of the water is just going to be hydrogen 1, H2O. It's going to be mainly, most of these hydrogens are hydrogen 1. A rare few of them are actually hydrogen 2. But you can, just like you did the uranium, you can enrich it, you can separate these out, and you can make D2O. Where in other words, it's predominantly hydrogen 2. Now it's very expensive. I did a lab in college where I had to use heavy water. It was in 1980, and I had to use 10 milliliters of it, and I think it cost, 10 milliliters in 1980 cost $120. Okay, that's a 10 milliliter graduated cylinder's worth. It was $120, and that was in 1980, so that's what, like $1,000 today.
Can you drink it?
Yes, it's 100% fine. It's got the, remember, isotopes have the same similar chemical properties. It's not radioactive. It's just, so, but if D2O, what would be the molar mass of water, just normal water? Well, how do we get the molar mass? Well, 2 times 1, right? Plus 16, this is going to be 18.02 grams per mole is what we said. Well, what would be the molar mass of D2O though? Go ahead. 20. Okay? Because it's going to be 2 times 2 is 4 plus the 16, so it's going to be 20 grams per mole. So we end up calling it heavy water because it just weighs more, because it's got more of the deuterium in it than it does naturally. Now, you're not going to, I mean, you don't just go and find a spigot with heavy water in it. You got to make that in the lab, and it's expensive and it's hard because it's so rare. You know, it's a challenge. Okay, it's just going to be used in a lab. It's going to be used for different research purposes. It's not going to be used for everyday living. However, Canada uses some heavy water. Now, it's probably not going to be pure heavy water. It's just probably going to be enriched with heavy water. But they use that as a moderator in their nuclear power plants in Canada. And I don't know what the difference is. It seems like light water is a lot cheaper. Okay, so heavy water. It's just got the H2. Does everybody understand that? Does that make sense? All right. So we know the main components. So that's really what I want you to know. We have the 7 layers here on the containment. This is just if anything does go bad, it's going to contain the radiation. And so the whole point is to heat up water, make steam, turn the turbine. Now, here's the deal. What do we do? What do we do with the fuel? This is the environmental part. What do we do with the fuel when it's spent? It lasts. You only have to replace 1/3 of those. Remember, there's 179 to 264 control rods in an assembly, in a fuel rod assembly. Okay, so there's 179 to 264, depending upon the design, of the actual fuel rods in one assembly, and there's about 179 assemblies in an actual reactor, and these are all your assemblies down here in the reactor. Okay, so they're all under the water, they're all doing their thing, but every 18 months they replace 1/3 of them. Well, what do they do with them when they take them out? Because they're still radioactive. They still have all the byproducts, those smaller isotopes, radiating beta particles. They're still generating a tremendous amount of heat. What do they do with them? Well, they got to put them in these pools. And this is what we were talking about yesterday. And Lucas saw me watching a video about what happens, you know, if you get into this pool. But it gets super hot. And in Japan, when they had the tsunami in Japan, do you remember that just recently? Not how recently, that was 10 years ago, huh? 2011 is when that tsunami hit. The problem is that this has to be cooled. That because these spent fuel rods are generating a tremendous amount of heat, and when it's not cooled, the water gets super hot, it evaporates, and then everything gets exposed. Well, when that tsunami hit, it knocked out all of the power. Well, they had backup generators, but they were on the ground. And so they all got flooded, so the backup generators didn't work. And so as a result, they lost all power, so they couldn't cool this pool anymore. And so it all evaporated. And so then they all just kind of got superheated. And then the flood waters just put all that radioactivity out across the whole property because they never dreamed they're going to have radioactivity. So it's not really so much the nuclear reactors that messed up. It was these spent fuel pools. And those fuel rods have to stay in there anywhere from 1 year to 20 years in this pool until they stop radiating enough to where they're cooled down, and then they're put into these concrete casts. And so all of those fuel rods. So these are, you can see the people right here. You can get an idea how tall. These are really tall. And all your spent fuel rods, and these are going to have to be there for thousands and thousands of years before they would be safe to even open up, because the radiation just keeps going on and on and on. Now, originally, the government said that we were going to have a place to put those out in Yucca Mountain, but Nevada politics ruled and they shut Yucca Mountain down, even though we spent $5 billion digging a hole. Government waste, right there, don't get me started. Okay, so anyway, all nuclear waste now is stored on site in these casks. Okay, so there's something about Yucca Mountain in your notes, but that's kind of moot now because that project is completely shut down. Okay? All right. So that is what you need to know about nuclear power plants. I just needed to finish that thought. The last thing for today is I want us to talk about what we call transmutation reactions. Transmutation reactions are how they make, all of these elements. How do you make an element? Transmutation, across, you mutate across. So like neptunium is made by bombarding uranium-238 with a neutron. It makes uranium-239, and then it naturally just decomposes by what kind of decay? Now, instead of saying an E, it's a B, so it's a beta. Okay, so that's another way of doing beta decay rather than saying E minus 10. Okay, but here, americium was made by taking plutonium. What is 2 out of, what is this right here? No. If it's got 0 protons, but the mass number is 1. Just what I want to know what this symbol, what this N01 is.
2 neutrons.
Okay? That's going to be a neutron. 0 protons, but the mass number of protons plus neutrons is 1. So this is the symbol for a neutron. The coefficient out in front means 2 neutrons. So to do this, notice 94, 2 times 0 is 2, okay? Is still, but you get minus 1 here. 95 minus 1 makes 94. 239 plus 2 makes 241, so it's 241. So the bottom numbers still add up. This 2 distributes. So you got 2 neutrons, so it's 2 times 1 is plus 239 makes 241. So you got 241 and 0 is 241. So here, this is an alpha particle. So you're bombarding plutonium with an alpha particle. And you're going to get 242 plus 1 makes 243. And then 96 and 96. So the bottom numbers still have to add up. The top numbers still have to add up. It's just bombarding. This is what they do in the lab to make elements, to kind of cause nuclear reactions. They're called transmutation reactions. Okay, so this is how a lot of these elements. This is the reactions that they did to make these, and they do those in those cyclotrons.
So the last number on the nuclear reaction is like the leftover.
This over here.
Yes.
That was talking, yeah, this is what, so they bombard it with this gets made, and then this is also just gets created. And so they just kind of do all kinds of crazy stuff. Now, you would never have to know how to write that technically, but you bombard this, somehow or other, they gotta make 17 neutrons hit that all at one time and get absorbed. I mean, I don't know how that's why, you win a Nobel Prize for discovering an element and stuff, because it's not easy. So what I want us to do is look at if we have some of those transmutation reactions, okay, like this. Not that one. Okay, well, what type of particle is that? Beta. So what would go right here? Well, what's the bottom number have to be? What minus 1 equals 93? 94. Okay? So you come up over here and you find 94 to be plutonium. Okay? What's the top number have to be? 239. Okay? So neptunium's going to make plutonium. So what are we going to get here if we do this one? We got 4 plus 2 is going to make 6. It's not chlorine. 6 is going to be carbon. Okay, and the top number is going to be what? 13. Carbon 13. Okay, so see if you can figure out what this one would be. What the bottom number has to be a what? 0. Top number has to be a 1. So if something is a 0 and a 1, what is it? That's going to be your neutron. Okay, that's your neutron. 0, 1 is a neutron. So that's a new symbol that we need to make sure we know. And then let's look at the last one. Okay. So this would be your spontaneous fission. This is just your uranium-236 blown apart. So you got a krypton 36. What does this mean? 3 neutrons. Okay, so the 3 distributes both ways. 3 times 0 doesn't matter, but you're going to have 3 at the top. So I got 36. There's nothing on the bottom. So what must this number be?
Y.
What number must it be? You go 92 minus 36, right? Which is going to equal 56. Okay? So you go 56, and you find element number 56 is barium. Okay? What's the top number got to be? Okay? It's got to be 236 is the top number, but then you have minus 94 minus 3. Okay, so you have the 3 here and the 94, so it's really minus 97. And so it comes out to what? 139. Okay? So you maybe want to do a calculation instead of just talking immediately. Think through an answer before you start speaking something out. Okay? So these are transmutation reactions. You just still make the top equal and the bottoms equal. You just need to know that this stands for 3 neutrons. If you have a coefficient out in front, that would be like 3 alpha particles if you put a 3 out there. And the 3 distributes to both the top and the bottom. So let's practice that for the rest of the day. Actually, I want us to do 2 things. Well, before I turn that off. I told you about Lees Meitner, and they have a great article in here on page 600 and whatever page, what page is that? 668 and 669. I want you to read that article just for historical purposes. in your textbook right here, the black textbook. Read that while I'm passing out a practice worksheet for you, just to practice some of these equations. All right. Thanks for watching. Again, hit that like button. Go Jags.